Hello everyone, I am Ashwant. Today I am going to present on the topic congestion control mechanisms in TCP, which is a key concept in the transport layer of computer networks. In today's world, where millions of devices are connected to internet, managing network traffic efficiently is extremely important. This is where congestion control plays a major role. In this presentation, I will explain what congestion is, why it occurs, and how TCP handles it using different mechanisms. Understanding network congestion. First, let us understand what congestion means. Congestion occurs when the amount of data being sent through the network exceeds its capacity. In more simpler terms, when too many packets are present in the network at the same time, the network becomes overloaded. A simple real life analogy is traffic congestion. When too many vehicles try to use the same road, everything slows down. Similarly, in a network where too many packets are sent, delays and losses occur. For example, when many people in a hostel use Wi Fi at night, the internet becomes slow. This is due to congestion. When congestion happens, routers cannot process packets efficiently, leading to packet loss and increased delay. Root causes of network congestion. There are several causes of congestion. The first cause is high traffic load. When multiple users send data at the same time, the network becomes overloaded. Second is limited bandwidth. Every network has a maximum capacity and exceeding this leads to congestion. Third is buffer overflow. Routers store packets temporarily in buffers, but when too many packets arrive, the buffer becomes full and packets are dropped. Finally, slow processing by network devices. If routers or switches cannot process packets fast enough, congestion builds up. For example, during major events like online ticket booking or IPL streaming, network experience heavy congestion. Impacts of congestion on network performance. The effects of congestions are very important to understand. First is packet loss. When buffer overflow, packets are dropped and must be retransmitted. Increased latency, meaning packets take more time to reach the destination. Third is reduced throughput, which means the rate of successful data transfer decreases. Another effect is retransmissions. Lost packets need to be sent again, which increases network load. This increases a cycle where congestion leads to more network if not controlled properly. This unpredictable behavior and frequent retransmission destabilize connections. TCP congestion control. To solve this problem, TCP uses sophisticated congestion control mechanisms to dynamically adjust retransmission rates based on network condition. Instead of sending data at a fixed rate, TCP continuously monitors the network using feedback form acknowledgements. This prevents network congestion collapse while ensuring reliable end-to-end communication. If the network is free, TCP increases its sending rate. If congestion is detected, it reduces the rate. This makes TCP adaptive and efficient. The protocol uses feedback from the network to determine optimal transmission rates, scaling back when congestion is detected and gradually increasing when conditions improve. Also, unlike TCP, UDP does not have congestion control. UDP sends data continuously while checking network conditions which can lead to higher packet loss. Key parameters in congestion control. Congestion window (CWND) controls the maximum amount of acknowledged data that can be transmitted at any time. Start threshold, also known as SS thresh, determines when TCP transitions from exponential growth in linear growth phase. Acknowledgement, also known as ACK, positive feedback indicating successful packet receptions, allowing window expansion. There are three important parameters in TCP congestion. First is congestion window or CWND. This determines how much data can be sent at a time without acknowledgement. Second is the slow start threshold or SS thresh. This defines when TCP switches from exponential growth to linear growth. Third is acknowledgement or ACK. These are signals sent by the receiver to indicate successful packet delivery. If acknowledgements are received regularly, TCP, TCP assumes the network is stable. If acknowledgements are missing, TCP assumes congestion. Slow start phase, building momentum. Initial window starts with small congestion window, typically 1 to 10 segments. Exponential growth. Window size doubles with each successful round trip time. Threshold check. Continuous exponential growth until reaching slow start threshold. The aggressive strategy quickly finds available bandwidth while avoiding overwhelming the network. In slow start phase, TCP begins with a small congestion window, usually one segment. For every acknowledgement received, the congestion window increases. This results in exponential growth. For example, it increases like 1, 2, 4, 8, 16 and so on. This helps TCP quickly utilize available bandwidth. However, TCP does not know the network capacity initially. So this rapid increase can cause congestion if continued indefinitely. This is why a threshold is used. Once the congestion window reaches this threshold, TCP switches to another phase. Interestingly, despite this name slow start, this phase actually grows very fast. Congestion avoidance, steady state. After reaching the threshold, TCP enters congestion avoidance mode. In this phase, the growth of the congestion window becomes linear instead of exponential. This means it increases slowly, usually by one segment per round trip time. The congestion window increases only by one segment per RTT, creating gradual controlled growth. This prevents sudden network overload while also maintaining stability and maximizing throughput. For example, instead of doubling like 8 to 16, it increases like 8, 9, 10, 11. This controlled growth prevents sudden congestion and ensures network stability. This phase is very important because it balances performance and safety. Fast retransmit and recovery, 4 to 5 minutes it will take. When packet loss occurs, TCP needs to react quickly. Instead of waiting for a timeout, TCP uses duplicate acknowledgements to detect packet loss early. If three duplicate ACKs are received, TCP assumes that a packet is lost and immediately retransmits it. This is called fast retransmit. After retransmitting, TCP enters fast recovery. Instead of reducing the congestion window to the minimum, it reduces it to half and continues transmission. This allows faster recovery and avoids restarting from the beginning. Detection: 3 duplicate ACK signals packet loss without waiting for timeout. Immediate retransmit: lost packet is resent immediately, reducing delay significantly. Window adjustment: congestion window reduced but avoids restarting from slow start. This mechanism provides response to packet loss while maintaining network throughput and avoids the inefficiency of restarting from slow start. Congestion window evolution and key takeaways. To conclude, TCP congestion control is one of the most important mechanisms that ensures stable and efficient communication in computer networks. Dynamic adaptation: TCP continuously adjusts retransmission rates based on network feedback. Efficient utilization: maximizes throughput while preventing congestion collapse. Essential infrastructure: fundamental to reliable internet communication and modern networking. As we have seen, congestion occurs when the network is overloaded with too many packets, leading to issues like packet loss, delays, and reduced throughput. To handle this, TCP uses intelligent mechanisms such as slow start, congestion avoidance, fast retransmit, and fast recovery. These mechanisms allow TCP to dynamically adjust its transmission rate based on network condition. One of the key strengths of TCP is its ability to adapt. It increases its sending rate when the network is free and reduces it when congestion is detected. This balance helps in efficient utilization of available bandwidth while preventing network collapse. These techniques are widely used in real world applications such as video streaming, cloud computing, and online services where reliable data transmission is critical. Video streaming services like Netflix, Amazon has examples like Netflix, Amazon, etc. Cloud computing and cloud gaming has services like GeForce and Google Stadia. These networks are widely used in real world applications. However, there are still some limitations. For example, TCP assumes that the packet loss always indicates congestion, which may not be true in wireless networks. This can sometimes reduce performance. Looking ahead, looking ahead, future improvements in congestions, future future improvements in congestion control may involve artificial intelligence and machine learning techniques to predict network conditions and more accurately and optimize data transmission. Overall, TCP congestion control plays a crucial role in maintaining the reliability, stability, and performance of modern computer networks. Another important point to understand is that TCP congestion control is not just a theoretical concept, but it is actively used in every internet communication we perform daily. Whenever we download a file, watch a video, or browse a website, TCP is constantly adjusting the data transmission rate in the background without the user ever noticing it. This makes the internet experience smooth and reliable. Also, Also, congestion control is not only important for performance but also for fairness. It ensures that no single user or application uses excessive bandwidth, allowing equal access for all users in the network. The concept of fairness is very important in shared networks such as college Wi Fi, offices, and public networks. So, why is this topic important to us as students and future engineers? Understanding congestion control helps us design better network systems and applications. For example, if we are developing applications that use the internet, knowing how TCP behaves can help us optimize performance. It is also important in fields like cloud computing, data centers, and distributed systems, where efficient transfer is critical. In modern technologies like 5G and high speed networks, congestion control plays an even bigger role because of the massive amount of data being transmitted.